Welcome back, everyone, to this part 2 of a 5-part series on mathematical modeling of organic contaminants and subsurface remediation. In part 1, we introduced some concepts of groundwater flow modeling. In this part, we'll look at some basic concepts of transport modeling. The behavior of a non-reactive contaminant in a porous medium is governed generally by 3 fluxes: an advective flux, a diffusive flux, and a dispersive flux. The advective flux is the flux of mass due to flowing groundwater, and just the product of the Darcy flux Q times the concentration C. The diffusive flux is a mass flux caused by a concentration difference or a gradient in concentration, and is the product of this concentration gradient times a diffusion coefficient times the porosity. Here the diffusion coefficient dd is the coefficient diffusion in the porous medium, and is the product of the tortuosity times the diffusion coefficient in water. The dispersive flux, or in this case the mechanical dispersive flux, is also a product of a concentration gradient times a mechanical dispersion coefficient times the porosity. And this mechanical dispersive flux is meant to reproduce the effect of unresolved pore scale variations in the velocity field. Here, the mechanical dispersive coefficient is the product of the dispersivity, which is a characteristic of the porous medium, which we'll define a bit later, and the velocity. Considering a mass balance of these 3 fluxes leads us to a derivation of the advective dispersive transport equation, where we're solving for the concentration C of our contaminant. This is the concentration in the dissolved or aqueous phase. Here, D is the hydrodynamic dispersion coefficient and is the sum of the mechanical dispersion and molecular diffusion. The solution to this equation, whether it's analytical or numerical, depends on the dimensionality of boundary conditions and initial conditions. So in this diagram up here, we have some boundaries to our system. We've defined the velocity field from our flow system. And likewise, we have to apply some boundary conditions with respect to transport along our boundaries, and we have to define the initial conditions of our system. So what are some of these boundary conditions? Well, as in for the flow simulations, we have a type 1 or Dirichlet condition, where we can fix the concentration. If a concentration is known somewhere, we can just fix it at that value. For instance, in a source zone here, C0, if we know what that source concentration is, we can just impose it along that boundary. Outside the source, whether it's an up-gradient boundary or here at the water table, if we know there's clean water coming in, well, we can impose a concentration of 0 on those boundaries. For example, another case, for example, if our contaminant source is internal, a dissolving non-aqueous phase, residual phase, for example, and all our boundaries, all our inflow boundaries here are clean water coming in, we can just impose a 0 concentration along those boundaries as well, type 1. A type 2, or Neumann, is where we fix the gradient, or a mass flux. This is most often applied in the transport context as a 0 gradient, where we fix the concentration gradient perpendicular to a boundary at 0. Here are just 3 examples. For example, we have a source zone here and a vertical flow downwards along a symmetry boundary, no flow boundary along the bottom. And along these 2 boundaries then, we can impose a 0 concentration gradient. Because basically you're saying that there's no dispersive flux across those boundaries. There are no flow boundaries in all 3 cases here, so we know the dispersive flux is going to be 0 across them. And the advective flux is by definition 0 because that comes out of the flow solution. Here's another example. We have some flow up gradient. Well, in this case, also, even if there's flow across this boundary, we can impose a 0 concentration gradient. And again, if it's far enough away from our source zone, then this is fine. There'll be no concentration ever reaching this boundary, so it's all right. And a third case here, we've got an outflow boundary. So here, a 0 concentration gradient also applies, even though there's flow across this. All we're saying here is that there's no dispersive mass flux across this boundary. But from the flow solution, the velocities here will give us an advective flux, so mass can still leave this boundary. So we see all these different contexts where a 0 gradient condition applies. It's quite general, and by default in most models, this is the condition that applies. We actually have a third type called a type 3 or Cauchy boundary, which is a mass flux condition where we impose a mass flux determined by the product of a flux times the concentration. Here's a little conceptual diagram here. We have a source zone here. If we know what this flux is crossing this boundary and we know what that concentration is, for example, a well-mixed reservoir, then we can impose this type 3. So this is a mass flux we're imposing on the outside of the boundary, So to equate the mass balance, on the inside of the boundary in the porous medium here, this advective mass flux must now be distributed into an advective component and a dispersive component. So that's the mass balance across this boundary here. So here's some context again. At a source zone, we can impose a third type boundary, and outside this source zone too, whether up gradient or along this boundary here, can also be third type. If it's far enough away, it can be zero gradient, as in this case. The advantage of a third type here is that we're not imposing the concentration along the boundary. We're imposing it outside the boundary, but the actual concentrations along the boundary remain part of the solution. So it's a little freer condition. We're not imposing the concentration now. We're going to let it build up naturally with this dispersive term. Just a little warning here: we should never apply a zero gradient condition next to a source zone. This will cause the source to be wider and cause some mass influx errors here. So those are our three boundary conditions. And here's just a blow up of one of those cases here. We have a source type 3 across the input boundary here. We have zero gradient where there's no flow, and we have a zero gradient also on the outflow boundary because we have an advective flux caused by the flow solution here. Just some 3 rules of thumb: keep boundaries as far away as possible from the plume, minimize the number of constrained or type 1 conditions, and look for and correct strange behavior at boundaries. One of the most simple ways to solve this equation is with an analytical solution. And one of the most simplest analytical solutions is called the Ogata-Banks solution. It was developed in 1961. And again, for the concentration C in the aqueous phase at a distance x and time t. And this is just some terms involving the complementary error function, exponential function, and another complementary error function here. Here, x is the distance from the source zone. Say we have a 1D column here, so x would be distance from this input concentration. T is the time. D is the dispersion coefficient. And our source condition here is a fixed concentration of C0. We have a fixed velocity V, and this applies for a 1D semi-infinite column for one component and uniform velocity. So this is the one restriction of an analytical solution, as we've seen. Homogeneous conditions, uniform velocity, and fairly simple geometry. For more complex geometry and heterogeneous systems, we need to solve our advection dispersion equation with a numerical method. One of the simplest methods is based on finite differences. And this is based on a Taylor series at a node I about its neighboring nodes. For instance, here we have a Taylor series defined in this graph here. We have concentration Ci, and this is our function. And basically the Taylor series give us estimates for these derivatives at different places, at different places in our grid. And for the simple concept here, let's just look at the diffusion equation. So we're interested in numerically estimating a first derivative and a second derivative. Well, if we take these two Taylor series, one expanded about node I minus 1, and the other expanded about node I plus 1. In fact, this gives us the forward difference here, which is forward with respect to Ci. So that's the estimate for this derivative, this first derivative. If we subtract these two equations, this gives us an estimate for the first derivative called a central difference. And here's a graphic interpretation of that. The central difference is just the slope here, and that's our estimate for the slope, which the true slope, what we want, is at position x here. So we really want this derivative, and this central difference gives us an estimate for that derivative. If we add these two Taylor series, we get an estimate for our second derivative, which interests us in this diffusion equation. And combining these two equations, at least for an explicit approach, where all our unknowns are at the old time level, we get an equation, a finite difference equation, for the concentration at node I at time j plus 1, or time t plus delta t, and it's a function of our known concentrations at the old time level j, and our neighboring nodes I minus 1 and I plus 1, as well as our central node Ci here, and our coefficient of dispersion, and a grid time step, and our grid spacing. Other options are implicit and central time weighting, which have some other advantage, some more advantages. As in all numerical solutions, finite difference has some stability constraints, accuracy constraints, and some geometric constraints. Another very popular method, numerical method, is called finite elements, and this is where we use an approximate function with a set of linear basis functions. So here in this graphic, we have a 1D system, x on the x-axis and concentration here. The blue line here is our function, our true function that we want to solve for, our concentration C. And the first step is to approximate this function by a set of linear functions between each node. So we've discretized the system and we've approximated this continuous function by a series of linear functions. And this is expressed by this equation here, where the concentration, the estimate now, the C hat, this linear function here, is the product of the nodal concentrations times these basis functions, which are just linear weighting functions. And then what we do is we replace the concentration in our advection dispersion equation by this approximate concentration. And now this will no longer equal 0. It will be some residual because it's an estimate. It's a linear approximate estimate of our true function. The second step in finite elements is to integrate the product of our function times a series of weighting functions. And this gives us n equations for solving n concentrations. So we have n equations for n unknowns, which we solve in a matrix equation. The primary advantages of finite elements versus finite difference is that is with regard to the geometry. We have much more flexible geometry with a finite element solution, as shown here. We can define our boundaries much better. Finite difference, you have these step functions in our grid. And it gives us a more efficient grid. So let's say you have a pumping well in here or some high concentration gradients that you need to resolve. Well, in a finite difference, you need to extend these elements right out to the boundaries, but finite element, you can resolve the mesh much more efficiently here around the area of interest. So that's the finite difference and finite element methods. This also has stability and accuracy constraints. A third method I'll just briefly introduce is called control volume. This is a very popular approach and is unique as it's based on a mass balance for a cell I. So it goes right back to the fluxes approach that we showed, where J here are the fluxes. So for cell I, or control volume I, just by writing a mass balance equation across the boundaries of cell I, so that the dispersive flux minus the advective flux across these two boundaries is our change in concentration. So here's our dispersive flux and advective flux. So the difference in the dispersive flux here is just the difference in our definition for the dispersive flux here. So it's coefficient of dispersion times the concentration gradient at across this boundary along the right minus the dispersive flux across the left boundary. And the same thing for the advective flux. You can write a mass balance equation for this advective flux. And all that equals our change in concentration over time. So with this equation, we reformulate it into this matrix equation and gives us a matrix equation for our unknowns, concentration I, as a function of concentrations at neighboring cells. Control volume is locally mass conservative, has a flexible geometry as well. A little more complicated in some cases to solve for flexible geometry, but it has good matrix qualities. It also has some constraints, accuracy constraints as well. And here's just a review of the main accuracy and stability constraints, which apply to pretty well all numerical methods. For flow, we have this constraint here that this ratio of conductivities and grid spacings should be similar. For transport here, these are the two main accuracy and stability constraints given by the Peckley number and the Curran number. So the Peckley number is just the product of the velocity and the grid spacing divided by the dispersion term. And for reasons I won't get into, but it's not too hard to understand, the Peckley number should be less than or equal to 2. If you make the simplification that the dispersion coefficient is the dispersivity times the velocity, this leads us to a method for estimating our grid spacing, delta x, as a function of the dispersivity. So this is saying as your dispersivity gets smaller, you really need a smaller delta x as well to resolve those concentration gradients that will appear. So we can define our grid. We can discretize our grid in space using the Peclet number, because we can choose ahead of time what our dispersivity will be. And the Courant number gives us a way of discretizing our system in time. So the Courant number is given by the velocity times the time step divided by the grid spacing. And for stability, the Courant number must be less than or equal to the Peclet number divided by 2. So with the maximum value of the Peclet number equal to 2, we can say that our time step must be less than the grid spacing divided by the velocity. So this gives us a way to discretize our system in time. We're going to be time stepping with our numerical methods. What happens if we don't respect these limits? Here's just some 2 examples. This first example is if we violate the Peclet number criterion. Here in black, we have a case where the Peclet number is 1, so this satisfies our criterion. Here's just an effective dispersive 1D system. We have these fronts at different times, 100 days, 200 days, and 300 days. We have a nice profile, a nice advective dispersive front. If we violate the Peclet number, let's say by changing our grid spacing, by increasing our grid spacing, here in red shows you what happens. Here's Peclet number of 10 in red for those same times, 25 days, 100 days, 200, 300 days. So now we're starting to get some oscillations here. Our maximum concentration has been exceeded. So that's a problem. And we also notice a change in slope here. And this is called numerical dispersion. It's just an increase in dispersion. We haven't changed our dispersion coefficient, but yet we're getting more dispersion. And this is called numerical dispersion, and it can be a little bit hard to find in a solution, in a simulation, because it looks like real physical dispersion, but can also be a problem. It can lead to washing out of plumes or lower concentrations in most cases. That's a Peclet number violation. If we violate the Courant criteria, here in black again, the exact same profiles, 200, 300 days, when the Courant criteria is respected, here 0.7. If we violate the Courant criteria, for example, if we increase our time step to 25 days, we start getting some very strange behavior here, some oscillations, so some very high concentrations beyond our maximum concentration. And we can also get negative concentrations too. Our slope here hasn't been too badly affected. We're getting the same slope. So not too much numerical dispersion, but these oscillations. And in fact, the solution can blow up too. It can become very unstable. So we really need to be careful with our grid and our time step discretization. Getting back to dispersion, here's two simulations which show the effect of transverse dispersion. Here are 2 plumes. We have a source zone here with flow and velocity here going to the right. In this top image, we have a transverse dispersivity of 0.1 meters. And here in the bottom figure, we have a transverse dispersivity of 0.5 meters. So 5 times higher. And look what's happened. Our plume is much wider. This could either be a plan view or a vertical section, for example. And here are just the 2 profiles through the center line of these plumes. To the center line, AA prime. Transverse dispersivity, the first case, dispersivity 0.1, here 0.5. So you can see that this plays a very critical role. Our concentrations have been reduced significantly here with our higher dispersivity. So we really need to understand or to choose our dispersivities carefully, especially if this was a transverse vertical simulation. Our transverse vertical dispersivity is very important. How do we define these dispersivities for our given site? Well, if we don't have any existing plume, our system is clean, we can base our dispersivities, first of all, on the scale of our system. So here's some data from a paper by Schultz-Makuch showing the longitudinal dispersivity alpha L versus system scale on a log scale here. So here, for instance, if our scale is 100 meters, let's say our maximum plume extent is going to be 100 meters, well, we can use this kind of graph to estimate a longitudinal dispersivity of, say, 1 meter. Once we have our longitudinal dispersivity, very simply, we can divide by 10 to get our transverse horizontal dispersivity, and divide that transverse dispersivity by another factor of 10 to get our vertical transverse dispersivity. So it's a factor of about 10 difference is a good estimate. If we already have a plume, of course, we can calibrate our plume, and by trial and error, we can find these dispersivities quite closely. But again, this is for a clean case, just based on system scale. So dispersivity will increase with scale. There are various other models use for that as well. Here's just some examples of what plumes might look like or what they should look like. Simulated plumes with different dispersivities, solving for our advection dispersion equation. Here are dispersivities alpha L 10 meters, alpha TB 0.05 meters. So evolution of a plume 2,000, 4,000, 6,000, 8,000 days. This is a vertical section. So we can see some characteristics here. Our dispersivity in the vertical dimension here, very small, 0.05 meters. And so we get these very high concentration gradients, and this is typically observed in the field, so this is good. We want to reproduce these vertical gradients. If the transverse dispersivity here was much higher, this plume would be completely washed out in the vertical direction. This becomes very important to simulate these high gradients, especially for reactive systems, because when the reactions depend on the concentrations, even a slight higher dispersion or mixing of these plumes will change the reaction rates considerably. Here's another example of our famous board and landfill plume. Here's a plan view and vertical section along the plume center line. Similar longitudinal dispersivity of 10 meters, transverse horizontal of 0.1 and a vertical of 0.01. And a coefficient of diffusion, of course, is incorporated in all these simulations too. So again, looking in the vertical section, look, we're getting very good resolution of our vertical gradients here. So this is good news. You want to see this in the vertical plumes here. Getting much good resolution of these gradients. The plume is well defined. It's not being spread out vertically. It's following the base of the aquifer very well, following the flow system very well. So these are the kind of characteristics you want to look for in a simulation. Make sure there's no boundary effects. Make sure your dispersion is controlled, that you're not getting numerical dispersion or oscillations. So those were cases for non-reactive contaminants. You've already studied linear absorption and linear decay. Here are just some examples of incorporating these into a model, into our advection dispersion equation. So with linear absorption, this retardation term, we can just divide the dispersion coefficient and the velocity by r in our model to simulate this effect of absorption. So here's a case of no absorption, r equals 1, advective dispersive profile. And at the same time, here's the profile at absorption retardation of 2. So exactly 1/2 the velocity and a corresponding reduction in dispersion. Similarly, we can add this decay term, in this case a linear decay, lambda, which is the natural log of 2 over the half-life. Here's our profile again, 1D system, it's actually 2D system, sorry, coming in from our source zone, profile along the center line, with no decay, and here's various profiles with different half-lives, a half-life of 100 days, 50 days, and a much faster decay rate, shorter half-life of 10 days. So these are quite simple in a linear context. We'll see some examples of nonlinear cases pretty soon. And most numerical models can handle this too. We can just to modify our terms here, add a factor of retardation and a decay term. Just looking at this decay a bit more, we can expand it. Here's just a summary of three approaches to simulate decay, and we can define it by its order. That is the exponent on the concentration term here. So this is 0 order. So our rate of decay is a coefficient times the concentration to the exponent 0. So it's independent of the concentration. First order is what we're all typically familiar with. Just a coefficient here times the concentration to the power of 1. So it's a linear, can be a linear term here. And then for other cases, we can include a Monod term. So this is a nonlinear rate, which varies between a 0 order and a first order, depending on this constant here. So here's just a comparison, useful comparison based on a paper by Beckens in 1998. Looking at the phenol concentrations in a lab experiment over time, just in a batch system, so there's no flow, at 2 different concentrations. So this is going to show the effect of this Monod. So in some cases, a 0 order might work, in some cases a first order, but in other cases, a Monod term is much better because it can switch between 0 and first order. So here's an example. Here's some data points showing degradation of phenol over time. So in this case, maybe a first order might work. Seems not too bad. A 0 order doesn't work. And here a first order with a different coefficient does not work either. So that's at a maximum concentration of 4. So maybe a first order might work here. Let's look at a higher concentration though, the same system, but just with a higher phenol concentration. Look at these first order rates here. This one's not very good because we haven't chosen the coefficients very well. Even this one, which is probably our best fit with the first order, might be okay up here, but if it doesn't match these lower concentrations. So really, and a zero order here, that seems to be a better fit to these upper concentrations. So ideally, we would like a Monod term, because now with the Monod term, at low concentrations, we can reproduce these lower concentrations here, these much lower concentrations. And with a higher concentration, the Monod term will also match these higher ones, the higher ones and the lower concentrations. So a Monod term is much more flexible. We have to define two constants, however, and we'll look at this in a little more detail in the context of biodegradation a bit later. Just a few words on coupling of a transport model with the flow model, various methods and reasons for coupling. So here we've just split our system into a flow domain. So we have to solve for a flow system, our heads or saturations perhaps, and we get our velocities. The velocities gets transferred to our transport domain, so we simulate evolution of our plume. And we might have a chemical domain linked to that as well, or a reactive domain. So first we can talk about transient coupling. So in many cases we have drawdown. Let's say we're pumping a mediation well and there's drawdown. So even our flow system is transient. And then of course our transport system will be transient. So this has to be coupled in a time step. So at every time step we have to solve for our flow and our transport. There are other cases where our flow domain, we want to simulate a steady state flow, maybe at an average condition over many years. So we can simulate just this at one time step and only time step in the transport domain. It can save us some time. Another type of coupling is a nonlinear coupling or feedback. For example, if our hydraulic conductivity depends on our NAPL saturation, if we have a non-aqueous phase liquid dissolving here, it's taking up pore space, it's dissolving, it's freeing up pore space, that's going to change our hydraulic conductivity. Well, our hydraulic conductivity is a parameter in our flow model. So we have, as it changes due to our NAPL dissolving in our transport domain, we have to update the flow system at each time step as that's happening. Similarly, if our density of our water depends on the temperature or the concentration of our contaminants, then as these are changing, we have to update our fluid density, which can change the flow system. So again, another example of nonlinear coupling. Or the porosity might change as well. If we have a dissolving mineral or NAPL, for instance, that might change our porosity again. So we have to couple all these. So that can complicate our life. It can increase our simulation time, but can be critical for these nonlinear type problems. Just some final words on calibration in the transport model context. Just some examples. As in flow, we can simply plot our observed concentrations versus our simulated concentrations. We try to minimize the spread here, so we get a nice 45-degree angle. In this case, a nice fit. We can look at specific breakthrough curves or profiles. For instance, here we're looking at concentrations versus time at observation wells. We can just look at this visually and try to match peak concentrations and basic behavior of our contaminants, either visually, or we can minimize errors quantitatively here. Here's another example of a breakthrough curve, in this case temperature. So we've got a good match to observe data here in time. We can look at fluxes. We can try to match fluxes over time. So here are some fluxes across a monitoring fence versus time, and we can look at different scenarios and interpret it that way. So these are some various methods for calibrating a transport model. And during the calibration, of course, we have all the transport parameters we can modify, reaction rates and so on. But we can go right back to the flow system as well and modify the flow system. Whether it's coupled or not, we can change the flow system to help calibrate our transport model. So that's the end of part 2 of our 5-part series. Thank you, and we'll look forward to seeing you for part 3.